Hi guys, welcome to our channel of Sciences and Mathematics. I'm excited today. We're going to try and tackle one of the problems in mechanics. This is a topic in physics, of course, which we had tried to discuss in summary in one of our videos. Of course, today we're going to see a summary of the concepts that we have discussed and try to see on how it is going to be applicable in this particular set of our problem. So without further ado, thank you and welcome. So in that case, as I have said, we are going to use the approach of trying to look at a summary of what we have already discussed, and then we shall try to see whether our points or the concept that we have discussed, how it can be able to be applied in this set of a question. So for that case, the question is: a car accelerates uniformly from rest for 20 seconds with an acceleration of 1.5 meters per second square. It then travels at a constant speed for 2 minutes before slowing down with a uniform deceleration to come to rest in a further 10 seconds. Sketch the velocity time graph of the motion and find A. Maximum speed, B. Total distance traveled, C. The acceleration while slowing down. So in this case, we can see that the set of our problem is centered around the topic of mechanics. And of course, as I said, we're going to use the strategy of trying to look at a few concepts that are going to assist us try to solve this kind of a problem. So under this, we are going to just look in a summary about the concept of linear displacement, velocities and acceleration. And then we shall look at a few, or just a summary also of equations of motion. So in this case, say that we shall look at linear displacement, and then we shall look at the concept of velocity and acceleration, and also we shall look at lastly the equations of motion, which are going to assist us try to solve this question. Of course, basically these three concepts we have already discussed in our previous video that we had an introduction to mechanics. So in actual sense, it's going to just be a summary. So in that case, first we're going to see some of the terminologies that we had already stated in our discussion. And the first one we're going to look at is what we call distance. So in this case, we said that distance, or just we talked about position, and said that position is just an infinitesimal, of course, point or location in space. And then we said about the concept of distance and say that a distance, or maybe in that case, is how far one travels from the point of origin. And regardless of direction, of course, in that case, can be used using maybe route R or P. So in this case, if I travel from point A to P using route R, that one refers to as a distance. But if I use a straight line, which is the shortest distance between A and B, which is represented by P, then that one will be referred to as displacement. So therefore, the difference between displacement and distance is that distance is how far you travel regardless of the direction, where displacement is where you are in relation to where you started. And then under this, we also talked about the difference between speed and velocity. And then we said that this one is a scalar quantity that only possesses magnitude, while this one is a vector quantity. So in actual sense, when you are trying to define velocity, you have to indicate in which direction this particular object or maybe a person is moving. So in that case, velocity refers to how fast and which way maybe an object moves, or the rate at which position changes. And in this case, velocity is given as change in displacement over time, which is given as delta S over delta T. And then for speed, this is a distance traveled over time. So we have said that speed in this case, of course, or distance is regardless of which direction. So if I say that I travel from point A to B using the route R, then the speed for that, it will be the total distance of R over the time taken in traveling from point A to B. So in this case, there's also a last concept that we have talked about, which is the concept of acceleration. So we also talked about the concept of acceleration. And in this case, acceleration is how fast you go. That is either you speed up or slow down. And it refers to actually accelerate at which velocity changes with time. So acceleration is given as a change of velocity over change in time. Of course, that one is going to be more clearer when we just demonstrate it using the concept of a graph. So in that case, those were some of the concepts that we have discussed in the summary, some of the relevant terms that we are supposed to use. And then we talked about, just in summary, about some of the specific graphs under the subtopic of graphing, which are used to represent, of course, these concepts that we have talked about. So in that case, we have two variables. That is a space, the demonstration of these concepts in a two-dimensional space. And we talked about acceleration time graph, or I can just indicate it as A, as we have already discussed about the concept, or maybe an initial that we can use for acceleration. So in that case, we can indicate that acceleration is measured in meters per second, and then the time, this is per second square. So, and then the time this one is measured in, of course, this is a time that is measured in seconds. So we just indicate time in seconds. So in this case, in graphing, of course, this is a representation of the relationship between acceleration and time in this concept of motion. So I said that if an object moves with a constant speed or maybe a constant acceleration, that refers to the variation in the change in velocity and time is constant. So in that case, that one is represented by that line, which, of course, this is for constant velocity. So in that case, for constant acceleration, we just indicate it using a straight line like that. So therefore, there are specific terms that we use. So in this case, we can say that this is uniform acceleration, while this one is non-uniform because it varies with the time. Uniform and non-uniform acceleration. So in that case, for an acceleration time graph, the area under this one represent what we call velocity. So the area, this area that is under here, I can just indicate it using A. So A represents the change in velocity. So the area under the curve of an acceleration time graph represents the velocity. So this was the first graph that we talked about under graphing. And then the second one that we talked about was the velocity time graph. Of course, we have looked at acceleration time graph. So the second one we talked about is velocity time graph. So we are going to see a coherence or just a consistency in the area under the curve, which is going to refer to different concepts. Of course, for the first one, for acceleration time graph, we have said that the area under the curve represents velocity. So in this case, for a velocity time graph, represent the change in velocity over time. And the gradient of this particular curve, of course, that is a slope, represent acceleration. So in this case, we're going to see two sets of graphs. The first one will be like that, and the second one will be like that. Of course, for the first case, we find that this is a straight line. Now for velocity, which is in meters per second, the first one for acceleration was meters per second square. So we will always be keen on the units or the derived units we are using for each and every aspect of this. So in that case, we have time, which is in seconds, and just indicate time in seconds for the units, and then we have same case velocity in meters per second, and then this is time in seconds. So for the two graphs, for the first one we have what we call a uniform acceleration. We have said that the gradient represents the acceleration. So if we were to represent uniform velocity from the velocity time graph, then it would just be an extrapolation of that, and then we have a constant line. For this one, it is with uniform velocity, while for the gradient of a velocity time graph represent uniform acceleration, that is, which means the object is traveling at a constant acceleration, of course. So for that case, similarly, the area under the velocity time graph, this is A, that one will represent what we call displacement. Displacement. We talked about displacement and distance. So for that case, for velocity time graph, the area under the curve represent what we call displacement. And then lastly, we shall look at our last, that is number 3, last set of graph. Oh, we haven't talked about the second one. Now for this case, for a velocity time graph that is showing some kind of an exponential graph, that one, of course, this is uniform acceleration, but for this kind of behavior, this is an uniform acceleration. Now for a velocity time graph with such a kind of an exponential nature, that's an uniform acceleration. So for the third set of graph that we were discussed, this was a displacement, so this is number 3, displacement time graph. Now for a displacement time graph, this is a displacement. Of course, we said that this one can be given as S. That is not for units. For displacement, the units are in meters. This is S just for the initial, but M is the unit for meters, and then time in seconds. So for a displacement time graph, the gradient there or the slope represent what we call velocity. So that is a displacement over time gives velocity. So in that case, that is a constant velocity. Of course, there's a graph already given for the velocity time graph, of course, which had an exponential nature. It just curves sharply. So in that case, if we were asked to find velocity, as we have said that the gradient for the displacement time graph represent velocity. This nature of a graph, of course, someone can be required to find the velocity at a particular point. So in that case, this is a displacement in meters over time in seconds. Now for the one that had a straight line like this, we said for the red one, that is, of course, velocity. And in this case, for the exponential one, somebody can be required to find velocity at a particular point. That kind of velocity is what we call instantaneous velocity, and it refers to the velocity of an object at a specific point in time. So in that case, we say that the object had traveled for 10 seconds, and then we are required to find its velocity. For instance, if this is the 10th second at this point, then we just do like that and try to find a gradient. This is change in displacement, and then this is change in time. So for us to find velocity at that particular point, then we'll have to find it. It is the change in S over change in t. Now this is known as instantaneous velocity. That is velocity at that point. So if it is maybe at the 5th minute or the 5th second, we'll just do the same by trying to find a gradient at that particular point. So that is what we refer to as instantaneous velocity. So in this case, as we have looked at different sets of graphs, these graphs are going to assist us trying to solve different kinds of problems depending on what we have been requested. So for this case, I think we have looked at a different set of graphs. Those are going to help assist us, of course, try to solve the graphs above. So in this case, lastly, we are going to look at the concept of a velocity time graph, of course, which is going to assist us derive some of the kinetic equations or equations of motion. So let's try to look at a velocity time graph, which, so this nature, so we shall have this, and then this point. So in that case, I'm going to use different initials to show specific points on this coordinate. So let's say that is a velocity, final velocity v, at this initial. An object starts from that point, this is the origin, and then it travels for the time t from 0, and then, okay, the distance between this point and this one, this is u, and then between this, okay. So in this case, we have said that for a velocity time graph, the area under the curve represents displacement. So in that case, when we have a velocity time graph, of course this is a time, and this is velocity. When we have a velocity time graph, this is meters per second, and this is seconds. So when we have a velocity time graph, the area under the curve will be denoted by the shaded area that I've indicated on the board. So in that case, from our regular figures, we can see that the area is made up of a set of two figures, regular figures. The first one is this, and the second one is this, of course. So we can easily identify them as figure 1 to be the triangle, a right triangle, and figure 2 is a four-sided figure, of course, which makes up a rectangle. So in that case, when we are trying to find the total displacement for this kind of a graph, you find that it is area under the curve. That is the area of the triangle plus the area of the rectangle. So now, before we move to that, you can find, we have said that v represents the final velocity for this case for an object that is traveling maybe for some distance, taking time t. So we have said that we're going to use the following initials, that is S for displacement, and then T is for time, and then A is for acceleration, V represents final velocity, U will represent initial velocity, and in that case, of course, we have demonstrated that this object starts from this point, that is the initial velocity, and travels for t seconds, and then it attains the final velocity at this particular point. So if we are requested to find the total displacement for this, I've said it's the area for A plus area for B. So in that case, let's try to see an equation that is going to represent, of course, the displacement that we talked about. So in that case, as we have said, this total displacement will be area under the curve which implies area of 1 plus area of 1 plus area of 2. So which represents, the first one is area of a triangle, which is given as half base times height plus length times width. Of course, the first one is the area of the triangle, and the second one is the area for the rectangle. So in this case, we find that S will be represented by a half. The base now for this kind of a triangle will be the point, the displacement from here to here, which is actually represented by time t. So in that case, that one we have t, and then we shall have the distance from here to here is of course v, that will be v minus u. So that is times the height, v minus u, plus length, which is t, times the height, which is t minus u. No, that is t, tu actually, because the length is t, and then the width is from 0 to u, so it is u times t. So S will be represented as a half, or just v minus u into t all over 2 plus ut. So in that case, we can just try to expand that kind of a formula and try to see. Of course, we said that for the first kind of an equation that we had written, we can simply, or basically simplify that by multiplying all sides of the equation by 2. Of course, we shall come up with that is S equals, of course this is 2S equals t into v minus u plus, this is 2ut. So in this case, we can just use the space here to try and find out the final answer. So in that case, we have 2s equals t to uv, and we can be able to simplify or just try to calculate the contents of that particular brackets, and then we shall have 2s equals ut minus v, and this is vt minus ut plus 2ut. So we try to look at like terms here. We have got this one and this one. So for that case, we should have 2s equals vt plus ut. So looking at this, t is a common factor for the right side of the equation. Then we can just simplify it and say 2s equals v into v plus u. So making s the subject of the formula, we'll have to divide by this numerical coefficient, which is 2 over 2. So in this case, then we shall have s, which is of course our displacement. So we shall have s given as, and just interpret this one and write it as u plus 2 over 2. So for that case, total displacement for this velocity time graph will be represented as S equals, that is initial plus final velocity over 2, which is average velocity times time. So that one will make our first equations of kinematics, or our first equation of motion. This is equation number 1. From the velocity time graph, we are able to use this information to find what we call displacement. So that's our equation number 1. So from that equation, we can be able to find, so we said from the velocity time graph, the gradient represents acceleration, so we can be able to use the information that is provided, which is the initial velocity and the final velocity and time, which is of course for initial velocity, which is u, this is initial, and then we have t, which is time, and then we have v, which is final velocity. Now from the equation that we had talked about, the gradient, which is of course going to represent the acceleration, which is acceleration equals change in velocity over time, change in time. So in our case, change in velocity will be final velocity minus initial velocity divided by time will give us our acceleration. So in this case, we can be able to express final velocity using that equation for acceleration by just trying to do a rearrangement. So in that case, I'll just do a rearrangement to that equation so that we have, if I multiply 2 by both sides of the equation, I'll have at is equals v minus u. So if I want final velocity, for that case, I'll have this u plus at. So in this case, this one will represent a second part of our equation of motion. So this one is for final velocity. This is equation number 2. So in that case, of course, we have just derived 2 equations from the velocity time graph that I've indicated. So and we said that if acceleration is given as change in velocity over time, then we can make t the subject of the formula here by writing, just doing a rearrangement where t will be equivalent to final velocity minus initial over acceleration. So in this case, when we have this first equation here, we can just do a substitution for t and try to see what product we will find for the first equation from this relationship of acceleration given by that equation. So in that case, we just come and do a substitution for t for this. So we shall have s is equals u plus v over 2 into, so instead of t we will use v minus u over a. So we will just do a multiplication for the numerators and the denominators, or just do a rearrangement as well. So in this case, when we're going to do multiplication for fractions, we're going to see that in that kind of an equation we can just make the common denominator and then do a rearrangement as such. So we will have, for multiplication, we will have s is equals u plus v into v minus u, and make this one a common denominator. So we shall have to remove the fraction by multiplying 2a by both sides. So we have 2as is equals u plus v into v minus u. So for this case, when we have such a kind of an equation, then we will have, of course, from multiplication, we will have this. This one will simplify to 2as is equals v squared minus u squared. So this one we can just give make v squared the subject of this formula, and then say v squared is equals u squared plus 2as. So this one will form our equation number 3. So the first one for displacement, the second one for final velocity, and the third one for the square for final velocity. So in this case, we have those 3 sets of equations of motion. And then this equation that we had used for our substitution here, of course, this is straightforward. We talked about the graph of that particular velocity time for acceleration, and we say that acceleration is equals final velocity minus initial over time. So this one forms our fourth equation of motion. Of course, we can start from this and say that this is the first equation, whichever kind of rearrangement, but this kind of a graph is the one that is going to assist us derive the four kinematic equations, of course. So in that case, we have the first one, which is, of course, as in the order in which we have done them. So the first one, displacement, average velocity times time. And then the second one for final velocity is u plus at. And then the third one, we said it is the square of v is equals u squared. This is initial velocity plus 2as, where a is acceleration and s is displacement. And then the last one we have said is this one. Of course, I've said the rearrangement, of course, or whichever position you may start from, as long as you are able to find those four equations and represent them from the velocity time graph. So in this case, this information that we have discussed is going to assist us in trying to solve our equation, because in as much as we are going to, of course, use the equations, you can see from the what we are required to find is speed, and then the total distance, and then acceleration. So in that case, of course, we have just tried to mention those aspects there. And then there was this concept of a car accelerates uniformly. We've talked about the concept of uniform acceleration. And then from rest, this is from the initial velocity for 20 seconds. This is acceleration. It then travels at a constant speed, of course, constant speed for 2 minutes before slowing down with a uniform deceleration. Deceleration is the negative of acceleration. So in that case, we're going to see how that one is represented. Of course, I've said it's negative, so we're going to see how it's being represented. With a uniform deceleration to come to rest in a further 10 seconds. Sketch the velocity time graph of the motion and find maximum speed, total distance traveled, and acceleration while slowing down. So in that case, we are just going to do away with the work that we have been doing here, so that we can just try to use the information we have been given to do that problem. So we're just going to list the information that we have been given, so that we are able to just use it appropriately in tackling this kind of question. So let's go to it again. We have been told a car accelerates uniformly from rest in 20 seconds. So we have said this is t, 20 seconds, and the acceleration here was 1.5 meters per second square. So this is acceleration, and this is time. Then it travels at a constant speed for 2 minutes before slowing down with a uniform deceleration to come to rest in a further 10 seconds. Sketch the velocity time graph of the motion and find. So in this case, we are just going to do the graph so that we can be able to represent this information in an appropriate way. So in that case, I presume that this is a velocity time graph. Of course, this is in meters per second, and this is in seconds. So in that case, they say a car accelerates uniformly from rest. So in that case, rest will be from this point, of course, of origin for 20 seconds. So the gradient for velocity time graph represents acceleration. So accelerates uniformly. The acceleration was uniform. We talked about non-uniform and uniform. So it's a straight line for uniform. Uniformly from rest for 20 seconds. So which means the time covered between here and here was 20 seconds with an acceleration of 1.5 meters per second square. It then travels at a constant speed. So in that case, a constant speed will be represented by a straight line for 2 minutes. So we have said that time is represented using seconds. Now for 2 minutes, it will be 2 times 60 in order to get seconds. So in that case, it consumed 120 seconds. But it's just to represent 120, the variable is in seconds. So 120 seconds before slowing down with a uniform deceleration to come to rest in a further 10 seconds. So in this case, if we travel from this point up to this one, it underwent this deceleration. I said that deceleration is a negative of acceleration, so which means we are going to represent it using a negative graph. So in that point between this one and this one, of course this was 120 seconds, it took 10 other seconds. So our graph might not represent the proportion, but just going to indicate that. So this is time in seconds. Slowing down with a uniform deceleration to come to rest in a further 10 seconds. Sketch the velocity time graph of the motion and find maximum speed. So in this case, we have just sketched a graph that represents the motion of that particular car. So in that case, the information we have been given, I've said it is acceleration, which is A. Acceleration equals 1.5 meters per second square. And then we have been given t equals 20 seconds. We also have u, which of course start from rest. From rest implies that u equals 0. So now we can find final velocity from this set of information that we have been given. Now that we were told that of course velocity from a rearrangement of acceleration is equals final velocity minus initial velocity over time, and final velocity is equals u plus at. Just a rearrangement of that formula in order to come up with that one. So final velocity is equals initial velocity plus at. Doing a substitution for this, we'll find that finding our final velocity is equals initial, which is 0, plus acceleration is 1.5 meters per second square times the time taken was 20 seconds. So in that case, that one will give us final velocity, of course, of 30 meters per second. So v is equals 30 meters per second. So in that case, that was the maximum speed from our first problem that we have been requested to find. So in the second one was to find the total distance traveled. So the total distance that was traveled can be calculated using, of course, two sets of equation. Since we have been able to find, we have this information now, we have v, which is 30 meters per second. And then, so in this case, we have two sets of equation that we can use. We said total displacement equals final velocity plus initial velocity. This is average times time. So we will see what we have in this, which is, of course, the initial velocity was 0, that is for u, and then final velocity was 30 meters per second, divided by 2, and then the time that was used in traveling was 20 seconds. So this one is going to be meters, so I've just deliberately, because of space, eliminated the units for that, but this one is going to be 300 meters. So that is the total distance traveled while accelerating, in that case between this point and this one. So this distance is equivalent to 300 meters. So bear in mind that it does not represent the total distance out of the curve, because this distance that we have just done represents the distance that was covered while the object was accelerating. So alternatively, of course, there's a second set of equation, but we'll just confine ourselves to that one. But the distance also that it traveled while it was undergoing a constant acceleration, of course, we can find that one using the constant acceleration. So if the final velocity was at this point and it continued traveling at that particular velocity, then we can say that distance. Now the second part of the distance was the velocity, which was 30 meters per second. Times the time it took, that is 120 seconds. So in this case, the distance traveled during the second phase, of course, will be equivalent to 3,600 meters. So looking at this, the first one is 300 meters, the second one is 3,600 meters. And then lastly, we'll find that the third pitch, when it was decelerating, the distance traveled, of course, will be given that the initial velocity was, when it started decelerating, was 30 meters per second, and then the final was 0. So in that case, we can just use still this equation of ours, and then I can just do away with this first set of information. So I just use that equation and say S equals initial velocity, that was 30 meters per second, plus final velocity, it came to rest, that is 0, and then divide by 2 times the time it took. So it took 10 seconds to come to rest. So the total distance traveled in that case would be 150 meters for, let's say this is A, B, C. So for A was 300, for B was 3,600 meters, and for C was 160 meters. For that case, for us to find the total distance traveled is A plus B plus C. So that is going to give us a total distance. S total is equals 4,050 meters. So that will be the total distance using that formula, of course, that we have said, and then using the second one here. So we have employed 3 kinematic formulas that we have talked about. This was our formula number 4. Of course, this was our formula number 3. Not certain about this, but this was our other formula. So these are the set of formulas that we have employed to, of course, find that set of equations for number A and B. So lastly, the acceleration while slowing down. So acceleration is change in velocity over time. So in that case, we are going to still use this first set of formula to find acceleration. So I'll just use that formula and do away with this. And then write acceleration is equals change in velocity over time. So we have been asked to find the acceleration while slowing down, of course, which is referred to as deceleration. That is why we have said that there is a difference between acceleration and deceleration, in that this one is a negative of that one. So we'll just use the information provided, in that the final velocity was 0 at rest, and the initial one was 30 meters per second, and then the time taken for that was 10. So acceleration, of course, will be given as negative 3.0 meters per second square. Negative implying that that is deceleration. Of course, that is moving from a particular velocity to rest, which is 0. So in that case, this is how we are going to use the information that we have already discussed in order to try to solve other kind of kinematic problems that we can be given maybe in other sets. Of course, we'll be doing others regularly as we go by, so that we get acquainted with the formula and other information that is relevant for us in this case. So for that, guys, this will bring us to the final set of our discussion. I hope we got a concept or two, and as we continue going to employ, of course, this kind of a strategy in doing one or two, we're going to get more of this, and it will assist us, of course, in developing that skill, of course, that we talked about, of problem solving. So for that case, this is the final bit. Thank you. Bye. May God bless you.